Hi, my name is João. I'm one of the students here in the Wireless Intelligence Lab, and in this video I'm going to show you as fast as possible how to reproduce the results for localization in Digital Twin MIMO Networks, a case for massive fingerprinting. We just got this paper accepted in ICC, the workshop in Synergies between communication, sensing and localization, and you can find the paper in this link here. And the results I'm going to show you how to reproduce are essentially three figures. It's going to be this one and these two. And then we have another table which it will come as a result, and I'll tell you where these results came from. Now the code, it's going to be in this repository, and if you want a very in-depth explanation of how this is going to work, I'm going to put a video with a longer explanation. This is going to be a very short video where I'll just show you how the results came to be and how you can get them. So here in the code, you'll get to the zip, download zip. I already have it downloaded here in my downloads. I extracted it, and then I essentially open Spider, which is my preferred IDE, and I navigate it to this folder. You can use, of course, any IDE, and importantly, to install the environment necessary to run this code, I placed some instructions here, and in the in-depth explanation video, which should appear here, I'll go through how to install. So if you want to really use the code and understand every line, this video that's going to appear here is for you. But this one, it's going to be really fast. So if you already have the Python environment installed, this is how the code is going to look like, and I'm going to essentially execute each cell. And here I open the DB main, it stands for database main, and it uses the RSSI DB library and the general utils. This DB main is all you should need. And our DeepSense scenario, DeepMIMO scenario, is in it's this scenario here called newsen. And I also include here the Blender model in case you want to open it in Blender and see essentially what it looks like. Yeah, the Blender model essentially looks like this. It's a very simple proof of concept scenario. And now we loaded the ray tracing scenario, and we are generating the channels from DeepMIMO, and then we are generating the database received powers in every beam and band. Now we are creating the database in this one, and just for checking that something is here, you can see some propagation. In this case, it's beam 0, but you can, for example, change to beam 12. I know beam 12 is closer to the center. Yeah, in this case, there's a reflection there, and you can also increase the resolution, for example, by changing here the cell size to 2. But for now, let us skip. I explain all of this. I explain every line in the code in the in-depth explanation video. For now, let us jump directly into the results. So to reproduce the results, you can, for the first one, you can run this plot here, this code here, position accuracy. I'm going to really reduce the number of positions for us to plot, just so it's very fast. It might be quite inaccurate, but we'll see. Yeah, very. It's even hard to believe it's the same figure. I placed all the figures in the results, and essentially, if you run for enough repetitions, because some averaging needs to happen, you will see something like this. This one also used a cell size of 1, so each little square is essentially 1 meter area. While in this one, it's 2 meters, and there's not enough averaging. I mean, even with 5, which is still quite fast, you'll see that this improves. Nonetheless, this is the code you should run, and you'll see that in line of sight there's less error than in non-line of sight. Of course, on average, because you might find very since we are sampling random distributions, might be different. Yeah, you'll see that it is getting there. And yeah, and so this is how you plot it. And to do the multi-parameter figures, which are these ones here, you have to write this. You have to execute this part. So let me put it in line of sight here, and let's run this. And while this is running, yeah, this is with 100 repetitions, so this should be quite close to what we get in the paper. In the paper, I think we did with 500. And this is outputting the results to the CSV path, which is here. And I already included the results, essentially the experiment that gave the results from the paper. But for now, let's plot the experiment with it. So I'm going to comment out this part, and our CSV path, it's the one with the 100 repetitions there. And by running this, you can tell it's not too far off this one. It sometimes oscillates a bit because of randomness. Sometimes including more measurements leads to including some noise in the system as well, so it might not decay perfectly. In this case, the beams are decaying quite nicely, but in any case, this is how you reproduce for the line of sight position, which it's this position here, and for the non-line of sight, you essentially change this 1 to 0, and that will make us take the non-line of sight position. And I'm going to run that again. And then once that is ready, which is in a few seconds, I essentially make the plot again. And right after this, I'm going to execute these two, which are the results. And I'm also going to open essentially the new CSVs we have here. This is for line of sight, because this is how we get the results from the table. Let me put it here. Yeah. So if we plot it now, yeah, this is the non-line of sight plot that we get here. But we did it with 500 repetitions and with a different seed, which I don't remember which one was, but yeah. Now, so we already executed the first figure and these two last figures, and now to get the table, how we got results from the table is essentially by we accumulated the experiments with it, because this essentially runs each of these points many times. And I accumulated these 100 experiments for each point, and I counted like the first 80% of the points with the lowest error, how much error was it there. And in this case, for the first iteration of 111, we got around 32 meters of error, which is 111 means measuring one beam in one band once, which is actually better than the one we got here. But as we, oh, actually 32, no, actually he matches quite well, this one, which is 80%. And with 90, oh, look, it turns out it's matching quite well. Yeah, but with 99, it's, well, not bad. I did when we do more repetitions, usually the results get quite more accurate. But these ones were quite alright. Maybe I could have got away with doing less repetitions. Yeah, but this is how you get the results. And I edited the figures a bit to move things, move the legend out of the way, for example. But that should be clear. So just to show you how the actual results look like, I have to, I'm gonna do them for the non-line of sight, just because that was the previous experiment with it, and that way we don't need to rerun some parts of this to make sense, because a lot of things depend on one another. So this figure should be exactly the same as the one we got in the paper. Exactly the same as this one. So I hope this was clear. I know it was a very quick video, and a much more in-depth explanation video is going to be in GitHub, in case you want to understand what each line does. And I have many more cells, and quite a few are for testing here, so I didn't go through those, and I also didn't explain the parameters. I do all that in the explanation video. Also to set up the environment. And if you are interested in running this code, actually let me know, because we are about to release a journal which has many more improvements upon this code, and so perhaps I can expedite on how fast we can make that code available, and I think it's going to be a better starting point. But let me know if you are interested in this. You can do that via my email, which is just my first name at asu.edu. And I thank you for watching. Let me know if, in case you have any questions, and looking forward to collaborate with you and then to see what you can do with this. Thank you for watching, and I hope you can reproduce all the results too. Thanks.